In this video I'm going to go through the two circle theorems that relate to the way that tangents particularly interact with circles. A tangent being a line which just touches the circumference at one point. And so theorem 6 says that any tangent drawn to a circle is perpendicular to the radius at that single point of contact. So we'll have a go at proving this one here. Let's draw ourselves a circle and then try and construct ourselves a tangent. So that tangent, let's call it PQ, and let's say that the point of contact with the circle is T. So what we're trying to prove then is that the line from O to T must be at 90 degrees, must be perpendicular to the tangent PQ. Right, so let's set this up by saying we've got T is the point of contact, to the tangent, so of the tangent PQ with the circle. And so what that means is that we said OT is a radius, isn't it? Alright, so what we're going to do here to prove that that OT and PQ must be perpendicular is actually a little proof by contradiction. Okay, so most of our proofs by contradiction have been to do with numbers, but let's do one here. And so what we're going to do is let's set up another point on here. We'll call that the point A, and we'll draw a line from O to A. And so let's start off by assuming that the line from O to A actually makes a right angle. So assume the right angle is at some other point A on that same tangent PQ. So in other words, what we're saying is assume the angle, what's that angle? Let's call it OAT, is 90 degrees. Okay, you can see where OAT is on the diagram. So what that would mean is that therefore the side opposite that must be the hypotenuse of a right angled triangle. So therefore OT is the hypotenuse of that triangle in there, which, what can we call that triangle? OAT. Alright, so following along so far, we've assumed there's a right angle at A, so in angle OAT. Therefore OT, the side opposite that right angle, must be the hypotenuse of triangle OAT. So therefore, we're saying that OA is shorter than OT, because all the sides, the other sides of a right angle triangle, are shorter than the hypotenuse. So therefore we're saying that OA is less than the length of the radius, because OT is a radius. So therefore we're saying, well, if OA is less than the radius length, then therefore the point A must be interior to the circle, mustn't it? You can't have a distance from the center that is shorter than the radius and get to some point that is exterior to the circle. So we're saying therefore A is interior to the circle, but it's not, is it? So, but then that means, or let's not say therefore, let's say, but that would mean PQ is not a tangent, because a tangent doesn't actually cross into a circle. So therefore then PQ is not a tangent. So if PQ was touching a point inside the circle, then it would no longer be a tangent. So therefore, by contradiction, by contradiction, the right angle must not be at A, the right angle must be at T. So we're going to get that same contradiction if we pick A to be at any other point other than at point T. Alright, so yeah, slightly different proof on that one. The next proof is for theorem 7, and theorem 7 is often called just the alternate segment theorem, and in fact that's what the syllabus calls it. But there is then below that a description for what the alternate segment theorem is actually saying. It's saying the angle between a tangent and a chord is equal to any angle at the circumference in the alternate segment. And there's our little symbol for that one in the yellow box there as well. So let's be clear on what this one's saying, and then let's go through and actually prove that it's always true. So first of all, if we draw a chord in a circle, that creates two segments, doesn't it? Now, unless unless that chord is the diameter, it's going to create a minor segment and a major segment. So segments are these bits here. There's the major segment and there's the minor segment in this particular case. And so what we're saying is that if we draw a tangent to the circle at one end of that chord, so if the point of contact of the tangent was right at the place where the chord touches the circle, then we get two angles between the tangent and the chord. So let's consider this one over here. So there's one of the angles that we get between the tangent and the chord. So this is saying the angle between a tangent and a chord is equal to the angle at the circumference, anywhere at the circumference, in the alternate segment. So since that angle between the tangent and chord is in the minor segment, then we're saying the angle at the circumference in anywhere in the alternate segment. So there's an angle. So all of these are angles at the circumference in. So as long as we can show that the angle between the tangent and the chord is equal to one of those, we've actually shown that it's equal to any of them, and that's by the one that we called theorem 3. Alright, so let's consider one case which is actually sort of easy to prove, and that would be if we take the line through the center of the circle. So let's consider the diameter in order to get our proof. So we'll call this tangent PQ, we'll call the point of contact T, and then we'll call these 2 points on the circumference the points A and B. So what have we got? We've said let T be a diameter. Okay, so that's the diameter of the circle. And then let's maybe label some angles in here. So we'll call that one there, well, let's call this one here X, because that's the one we're going to try and show is equal to angles in the alternate segment. So we're going to let angle ATQ, isn't it? So ATQ is going to be equal to X. And then the other one there is angle BTA, and we're letting that be equal to Y. Alright, so then we've got that the angle, TBA, let's say, so TBA, which is the angle that we're sort of interested in over in the alternate segment. So angle TBA is going to be 180 minus, well, it's minus 90 first of all, because this is an angle in a semicircle, therefore this one here has to be a 90 degree angle. So we're going to take away 90, and then we're also going to take away Y. So we've got a couple of theorems that we've used there. One is that the angle in any angle in a semicircle is a right angle, and the other one is just the angle sum of a triangle is 180. So 180 take 90 take Y is just equal to 90 minus Y. But also we know that in fact, angle X is equal to 90 minus Y by theorem 6, which we just proved, because OT is a radius. So, because we've got the angle between a radius and a tangent, which is always 90 degrees, therefore X and Y must add to 90. So therefore, we've showed that angle TBA is equal to X. And because we've showed that for one angle on arc AT, it must be true for any angle at the circumference in that segment. So maybe I'll just state that there and say this will hold for any angle in the same segment. Any angle in the same segment by, let's just say by that one there. Alright, so that's the proof of those two circle theorems with tangents.